So you're gonna have four propellers here, and these four propellers for the drones, but the drones has four propellers. So basically, the drone has four propellers, and the four propellers are what used to take lift. Three propellers. So you have three propellers. We're gonna work together to as one propeller. Following the old design. So the old design is the old image. Where is the old picture I drew? So find it. But you're gonna have three propellers and three the one big propeller, but it was gonna be like a toe kind of a model. So basically think of so you have a monkey swinging on a branch, and the monkey has four toes, and one fake toe, one toe that's not a toe, one grappling toe. So the space between the monkey's toes is a toe there, but that toe's not a real toe, just a space. Well, that's toe, just because those grabbing branches are the purpose. That's a toe, because that's kind of the toe. So it's like an avatar. If you think about Avatar, the same thing for an Avatar. Avatar has like a Avatar the movies, not the Airbenders. Avatar has like the kind of the blue. They have toes, but they have they have four toes, but they have one spare toe. That's a fifth toe. But that fifth toe is basically in between the legs, and the same for the wings. So the wing is the same thing. So you have three propellers, but you have when they join together, when it stems together, it's into a module. It's one module, and one module can be assembled and disassembled. So because you can assemble it into a kind of you can disassemble the model. You can separate the three propellers. You get into different configurations. You have a sparse way of modeling. So there's like that's like an extra propeller. And because you can join them properly into something, join them, control the trajectory of how your planes fly in the air. So this is a model of dealing with kind of area kind of phenomenon, like a wind turbine, things like that. In rain, but it's like a drone that flies, and it's gonna be waterproof. Of course, it's gonna be waterproof at school, or thunderproof. So let me just draw this one. Um, right, yeah. So these are humanitarian drones that fly. So basically, let me not label it. So what's my pen? So more likely they're gonna have uh 3 centimeters by 3 times 2 centimeter, 3 by 3 centimeter propellers. Let me just write 3 by 3 inside 3 by 3 times 2. 3 times 2, 3, 3 times 3, 3 times 3, and so you're gonna have 3 times 3. So these are the propellers. So it looks like now. So it looks like you're gonna have three propellers. You're gonna fly adjacent to it. So you're gonna have three propellers and spinning. So the top down model. So you're gonna have something around it. So basically, these are components that can stabilize this. So so you can have them. They have to contain. So these components have to modulate it. So the modules are so I'm gonna say, drink some water. Ooh, ooh. So let me explain something now. So you're gonna have the phase of takeoff. So the phases are like this. So you're gonna have the phases. So you're gonna have you're gonna have a launch phase. You're gonna have a takeoff, a takeoff. So the three propellers have to get to some altitude. They have to get some altitude to join. So join the three propellers into one propeller. So they can deal with some kind of air friction. My goal is to take the airplane to 100, 1,000, 1 kilometer 100 meters above the ground, and be able to fly 100 meters above the ground. Uh, no, the gun can shoot them down. Let's go. To go 300, 250 meters above the ground to 500 meters, to 1,000 to 1 kilometer above the ground. So drones are not really in that kind of category, but that's what I'm trying to do. So 250 meters above the ground and 1,000 meters, 1 kilometer. And this electrical project works. So the drone has to assemble module. So you're gonna have a module. So you're gonna have the phases and the pipeline. So you're gonna have the procedure, and you're gonna have the process, and you're gonna have the pipeline. These are keywords, by the way, that I'm trying to define in the sticky protocol. So the drone takeoff procedure is a process. A procedure is a main characteristic of a system, and a pipeline is defined some kind of modular component instruction. So you're gonna have some kind of modular component instruction. So the process is that a process is a four-way FFI, a 2x2 way FFI, a 2x2 foreign function interface. So it's a square. It's a square. A process is defined by the kind of instruction, the protocol, and SIGIT protocol itself for takeoff. Now, remember, this is basically the human out the loop system for ontological Bayesian intelligence, or an AI system that knows itself. Ontological means me, myself, and I. I know my states, I know myself, I know what I'm doing. Bayesian means based on the probability. And intelligence means AI intelligence. Primarily, I'm trying to separate processes which are 2x2 foreign function inches by like a squares, because they can go flow both ways in a bidirectional manner. And my battery is running low now. Sorry, guys. And achieve separation of concern for my computer hardware. So gonna have a two-way foreign function interface that's defined. So the aircraft can fly. My aircraft can fly. So you're gonna have a propeller. Before we're gonna focus on process, the process is the protocol itself, like it is defined in NSIGII aircraft education for takeoff. Now, the takeoff position is what the wing should do, what the wing should do, what the propeller should do. So it includes all the components of the module. So I'm going to start bottom up. So the modules are here include the aircraft propellers, which I'm going to speak about the propellers. So, for example, the propellers are part of the module that take off. So the propellers turn on, turn on, turn on. They initiate or turn on. Or invoke the driver. Invoke the driver. The process of them invoking the driver is two-way function. So every computer controls with a binary, so it's a binary, so it's not a process and not a procedure. And a procedure is a two-directional. So basically, a procedure locks is a two-way FFI. So it's a rectangular system. So two systems are talking to each other, two or more systems in a it's a rectangle basically, because you have all squares, all binaries are drivers, not all drivers are binaries. All squares are rectangles, not all squares are triangles, not all squares, not all triangles are squares. All two-way communication is bidirectional. This bidirectional topology, this bidirectional requires the ontological Bayesian assistance, OBI AI, to have a software development kit. And this is basically not a weapon, because FPC is a human out-loop, so autonomous system. And it's a trial that's okay. So go human out-loop systems. So you're gonna have a two-way FFI, And you're gonna have two by two way FFI, which is basically a binding, and a two by two two on two, which is a two by two, which is two on two, which is a two on two, which is a rectangle. So you have a two way communication, but they are digital. It's a process. So they have two main entry points. Because they're two on two system. So if a rectangle is two on two, that means you have it's a driver can execute topology. Now the topology depends on the procedure. So procedures have two main entry points for consumption. The main exe written in Go, and one written in Python, and they determine how they orchestrate via the protocol Alpha Lima Alpha Indigo P for Papa, Alpha Lib protocol Alpha Lima Alpha Indigo B for Bravo B for Papa O for Oscar Alpha Lima Y for Yankee C for Charlie A for Alpha Alpha Lima Lib protocol, which was for polyglot system. I made that. The goal of this is to have the bindings use give orchestration, and the drivers give instruction, determine instructions via main.exe. So the drivers are used to execute instructions on the machine, but the driver they did a package, they did like a Rust binding, so you can have a Rust package which basically has executable instruction set via the workspace of Rust. So, for example, if you have Go Python, if you have Go and Python, you have a executable main.exe that are peer-to-peer, a peer-to-peer network. And this server doing jobs to orchestrate the driver via mesh rings, via mesh topology of orchestration. So you're gonna have two drivers talk to each other basically, and one's doing one job, one driver is doing one task, like operating the wings, while the other is doing another task like task scheduling. Like, so if you want, if it was some, if it was different X means they are one main.exe from Python is doing is lifting, is taking off, is doing takeoff. Circle or north NOUGHT is doing initiation. And this is going to the power job via an edge computing interface, which is basically a scheduling operation. So they can consider two jobs: takeoff and takeoff and takeoff or turn on, whatever, takeoff of flight. Take off, take off, take on. Basically, the two jobs are two procedures that run via the standard pipeline. It's not a boot sequence for this computer to initiate. It's an initiation sequence to go to take off, and that's what it takes up. But this is defined so safely protocols can fly in the air and do kind of system of takeoff and So that's the goal there. So this is what I'm written down here. Let me finish my drawing here. So you're gonna have a square, a triangle, and you have the two main issues. So you have a peer-to-peer network, and the peer-to-peer network is just one example. I'm giving an example. You're gonna have ring topology, bus topology, mesh topology, but this will have execution main.exe. This will have a main.exe. Now, but it's basically you gotta have a binding to binding coherence, a driver to driver coherence, and basically no coherence cause. Because you gotta have a measure of the binding to binder, driver to driver, and the whole kit itself. The software, basically you gotta separate into modules, and the modules are what is initiated into the system. Like initiate the aircraft wings from a namespace. So Netflix will standardize very well. So this determines what gets initialized. It's like using namespace STD, using namespace module, using module wingspan, wing. Like if you take flight, taking flight, using what's the propeller, using modular propeller, and that should use the propeller models to to determine how the aircraft so programmatically there's one-to-one coherence, one-to-one mapping via this Biden square, Biden reconciliation model, and you have a Biden driver, and you have via software development kit. So via as a software development kit for initialize, so everything can be kind of solved. You have the initialization of the system based on human and loop, human out loop, and human on the loop system. So let me just, without further ado, let me continue this. So you're gonna have you're gonna have this here. Well, this is a mess, but you get the idea. So this is to the one wing in total. So this could be one whole wing that's spinning around two. So you're gonna have, so you have four wings in total because basically you have four wings instead. So it's better just have four wings instead of three wing ensemble. So basically you have four wings and the four, so get for one big one. So you have one wing, one big wing, and three smaller wings. That's what I mean. So you have one big wing and three smaller wings. So that's how it looks. You get one big wing. So look at my hand. So one big wing that's on the bottom that has three smaller wings attached to it. And this one can spin. And it takes to spin. So again, it's space to spin kind of in a way that's heterogeneous, homogeneous. So again, it's spinning in the air and sticking off of the other propellers. So this is how it looks, guys. Let me try and rub it out. I'm trying to be more careful with my drawing. You have 4 weeks total. You So this is what it looks like. So you have one big wing and three smaller wings. So these are the three smaller wings. So you have basically be half the span of this. So they will spin it in a kind of way, but spinning to stability. And that's the but this one shuts down. This one is not needed. Basically, the big wing in the middle is not needed, basically. But it's gonna only we're going to do is some altitude that will be needed. So that was basically you can't turn the middle wing on until the big one is needed. So the biggest wing in the middle is not needed per se. It's just that it's needed when you have when you're trying to get more lift into the air. But it's not gonna turn on when you need it. It's gonna turn on when you need it. When you need it. That's what I'm saying to you guys. Let me shut this video down.